Okay, Assalamualaikum warahmatullahi wabarakatuh and good afternoon. Today we're going to continue on the transport protocol layer. Last week we already discussed on the UDP, User Datagram Protocol. So today we're going to discuss on the TCP, Transmission Control Protocol. So TCP and UDP differ in many ways. The most fundamental difference is the UDP is connectionless while TCP is connection oriented. UDP is connectionless because it sends data without even or ever establishing a connection. So UDP, they will just send the data without any connection establishment. TCP is connection oriented because before one application process can be sent data to another, the two processes must first handshake with each other. So means they require for TCP data connection, the client and server, firstly they need to establish connection first, and then once the connection established, then the data can be transferred. After the data has been transferred, the server will send acknowledgement to the client, mention that the data has been successfully received. So TCP connection provides full duplex data transfer. So this is TCP segment structure. So the first layer has a source port and destination port. So these two is required in transport layer protocol, either UDP or TCP, and then it has a sequence number. So if the data is longer than 32 bytes, it needs to be separated by segments. So that's why it needs sequence number to know which data come first and which data is the last. And then it has also acknowledgement number, so that acknowledgement is required because the clients need to know whether the data that the client sent is received or not. And then there's a header length, window size, checksum, and we already discussed it last week, option, and the lastly is the data that we're going to send. So the principle of reliable data transfer in TCP, we're going to discuss it, this data transfer, the principle of it. So with a reliable channel, no transfer data bit are corrupted. So there's no flip 0 to 1 or vice versa, or the data loss. And all are delivered in order in which they were sent. So this is precisely the service model offered by TCP to the internet application that involve it. So TCP is a reliable data transfer protocol that is implemented on top of an unreliable IP end-to-end network layer. So this is an example of the end-to-end data transfer. So A here is a reliable data is using reliable channels. So if the channel is reliable, we can use UDP because we know that there will be no error uh, that the data sends or lost data. However, in reality, the channel might be unreliable, so might be there's a cable loss and so on. So we can call it unreliable channel. So that's why we need a transfer layer protocol, TCP, so that they will check the data error and can correct it. Okay, let's look into these two consideration for the reliable data transfer. The first is reliable data transfer over a perfectly reliable channel, RDT 1.0, and reliable data transfer over a channel with bit error, RDT 2.0. So we're going to look at RDT 1.0 first. So RDT 1.0. So we first consider the simplest case in which the underlying channel is completely reliable. So if you look at this figure 1, a sending side. So the sending side of RDT simply accept data from the upper layer, which is the application layer, via the RDT data, and then put the data into a packet and send the packet into the channel. So in practice, the RDT send data event would result from a procedure called RDT send by the upper layer application. So on the receiving side, the RDT received a packet from the underlying channel via the RDT packet, remove the data from the packet, and pass the data to the upper layer. So the RDT packet event would result from a procedure called RDT RCV receive from the lower layer protocols. So in this simple protocol, there is no difference between a unit of data and a packet. Also, all packet flow is from the sender to the receiver with a perfectly reliable channel. So there is no need for the receiver side to provide any feedback to the sender, since nothing can be wrong. So this is the perfect reliable channel. So there's no data loss, there's no data error. So we look into the RDT 2.0, where RDT 2.0 reliable data transfer over a channel with bit error. So this is more realistic model compared to the RDT 1.0. So the message in the protocol will use positive acknowledgement and negative acknowledgement. So positive acknowledgement shows it is okay, and negative acknowledgement shows that please repeat that, means that you need to send the data again to the receiver side. So this control message allows the receiver to let the sender knows that what has been received correctly and what has been received in error does require repeating. So in a computer network setting, reliable data transfer protocol based on such retransmission are called ARQ, Automatic Repeat Request Protocol. So what is an ARQ protocol? So the protocol provide three main function. First is error detection. So mechanism is needed to allow the receiver to detect when bit error has occurred. Receiver feedback. In this case, whether or not a packet has received correctly, the receiver to provide explicit feedback to the sender. And lastly is the retransmission. A packet that is received in error at the receiver will be retransmitted by the sender again. So this figure shows how exactly RDT 2.0 works. So if you look at this figure 1, this is the sender side. So it added a acknowledgement or NAK. NAK is negative acknowledgement. So ACK is positive acknowledgement. So the sender send a packet to the receiver, and then it will wait for the positive acknowledgement or negative acknowledgement before it will send another data again. So this protocol is also known as stop and wait. So it will stop the transmitted data and wait for the acknowledgement. That's why it calls stop and wait. And then at the receiving side, the data is received, and then it will check for the error. Is it corrupted? The data is corrupted or not? If it's corrupted, it will send the negative acknowledgement. If there's no corruption to the data, it will send the positive acknowledgement to the sender. So it will repeat again and again in the sending and receiving side. The RDT 2.0, which using stop and wait protocol, has a fatal flow. For example, if you want to send a data from this is USA country, so from California to New Mexico, it's basically you require 15 milliseconds for one data to transfer from these 2 points. So it's quite a delay. So if you send a lot of data, so maybe the internet will look very slow. So that's why there's a pipeline reliable data transfer protocol. So this solution to this particular performance problem is rather than operating in a stop and wait manner, the sender is allowed to send multiple packets without waiting for acknowledgement. So they don't need to wait for acknowledgement to send another data. So we can send multiple data in one time. Pipelining has several consequences for reliable data transfer protocol. First is the range of sequence number must be increased, since each in-transit packet must have a unique sequence number and there may be multiple in-transit and unacknowledged packets. So and then the second is the sender and receiver side of the protocol may have to buffer more than one packet. So minimally, the sender will have to buffer packet that have been transmitted but not yet acknowledged, and buffering for correctly received packet may also be needed at the receiver as discussed. So that's why two basic approach toward the pipeline error recovery is identified. The first is go back end and the second is selective repeat error recovery. So we're going to discuss this in the next slide. So before that, we'll look into the example of the stop and wait protocol and pipelining protocol. So on top of this figure is the stop and wait. So they will send data and the sender send the data and wait until the acknowledgement received, and then the sender will send another data. However, in pipeline operation, you can send multiple data in not all, but there's a limited number using sequence number, and then at the same time you can send after a number of packet, you can send another packet after they receive the acknowledgement. So in this pipeline application, we can avoid delay for the data. So we're looking at the error recovery protocol for the pipeline operation. So the first is the go back end GBN protocol. In a GBN protocol, the sender is allowed to transmit multiple packets when available without waiting for an acknowledgement, but in constraint to have no more than some maximum allowable number, which is n, of an unacknowledged packet in the pipeline. So for example, from this figure, the data can be sent in multiple in a parallel way. However, there's a n number allowable packet that can be sent until the sender receives the acknowledgement. For example, if n is equal to 10, so only 10 data can be sent at one time. So another the 11 or 12 data, this data, the 12 and the 11 and the 12 data can be sent once the acknowledgement from the first parallel is received by the sender. So we look at the selective repeat or SR protocol. So the GBN protocol allows the sender to potentially fill the pipeline with packet, thus avoiding the channel utility problem we note with the stop and wait protocol. There are, however, scenarios in which the GBN itself will suffer from performance problem. In particular, when the window size and the bandwidth delay produced are both large, many packets can be in the pipeline. A single packet error can thus cause GBN to retransmit large number of packets, many of which may be unnecessary. So for GBN, if uh, one packet from a number of packets it has an error, so the GBN will retransmit all the packet. So for example, the sequence number n is equal to 0. So if one of the packet has error, so GBN need to send all 10 packet in another transmission. So it is waste of time and unnecessary. So that's why the selective repeat SR protocol is invented to solve the problem of the GBN protocol. So in this figure, there are two examples. The first is go back N operation and the second is the SR operation. So let's look into the go back N operation. In this example, there are 5 packets sent, N equal to 5. And then if you can see it in here, packet 2 has an error which the transmission has lost. It means that the receiver will not send acknowledgement of packet 2 to the sender. And then the sender knows that if the receiver didn't send the acknowledgement, it means that the sender knows that the packet 2 is not being received by the receiver. So after the n equal to 5 means that after packet 5 it will retransmit back the packet 2. However, in go back N, the sender will not only send the packet 2 but the packet after it. So means all the packet after the packet 2 will be sent again. So it is unnecessary and require a lot of time, which cause delay. However, in SR operation, if the sender knows that the packet 2 is lost, only the packet 2 is retransmit back to the receiver. Other packet will not be sent again. So that's why they call selective repeat operation. So selective repeat SR protocol avoid unnecessary retransmission by having the sender retransmit only those packets that is suspect were received in error or lost or corrupted at the receiver. So this individual as needed retransmit will require that the receiver individually acknowledge correctly received packet. So a number size of n will again be used to limit the number of outstanding unacknowledged packet in the pipeline. So that's all for the transport protocol layer. If you have any question, you can WhatsApp me. And after this, we're going to discuss on the next chapter, which is the chapter number 5, network layer protocol.